Hello? Can you hear me? Hello? Okay, can you guys hear me? I have the stream on now. And yeah, I'll be reading the operating system's book again. Let me change to. Oops. Did I have anything important here? Nope. Anyways, so I would be reading about. I will be reading this chapter. It's called Virtual Machine Monitors. I have no clue what this is. And I think this chapter is deprecated. Yeah. And I think I will read this chapter, and this will be the last chapter in the on this topic. Dialogue on virtual machine monitors. So now we are stuck in the appendix, huh? Yes, just when you thought things couldn't get any worse. Well, what are we going to talk about? An old topic that has been reborn: virtual machine monitors, also known as hypervisor. Or like VMware, that's cool. I've used that kind of software before. Cool indeed. We've learned how VMMs add yet another layer of virtualization into systems. This one beneath the OS itself. Crazy and amazing stuff. Really. Sounds neat. Why not include this in the earlier part of the book then on virtualization? Shouldn't it really go there? That's above our pay grade, I'm afraid. But my guess is this. There is already a lot of material there. By moving this small aside on VMMs into the appendix, a particular instructor can choose whether to include it or skip it. But I do think it should be included because if you can understand how VMMs work, then you really understand virtualization quite well. All right, then let's get to work. Years ago, IBM sold expensive mainframes to large organizations, and a problem arose. What if organizations wanted to run operating systems on on the machine at the same time? Some applications had been developed on one OS and some on others, and thus the problem. As a solution, IBM introduced yet another level of indirection in the form of a virtual machine monitor, also called a hypervisor. Specifically, the monitor sits between one or more operating systems and the hardware and gives the illusion to each running OS that it controls the machine. Behind the scenes, however, the monitor actually is in control of the hardware and must multiplex running OSs across the physical resources of the machine. Indeed, the VMM serves as an operating system for operating systems, but at a much lower level. US must still think it is interacting with the physical hardware. This thus transparency is a major goal of VMMs. Thus, we find ourselves in a funny position. How can OS has thus far served as the master illusionist, tricking unsuspected applications into thinking they have their own private CPU and a large virtual memory, while secretly switching between applications and sharing memory as well. Now we have to do it again, but this time underneath the OS who is used to being in charge. How can the VMM create this illusion for each OS running on top of it? The virtual machine monitor must transparently virtualize the machine under the OS. What are the techniques required to do so? So, first, the motivation. Today, VMMs have become popular again for a multitude of reasons. Server consolidation is one such reason. In many settings, people run services on different machines which run different operating systems or even OS versions, and yet each machine is lightly utilized. In this case, virtualization enables administrator to consolidate multiple OSs onto fewer hardware platforms, and thus lower cost and ease administration. Virtualization has also become popular on desktops as many users wish to run one operating system, say Linux or Mac OS X, but still have access to native applications on a different platform, say Windows. This type of improvement in functionality is also a good reason. Another reason is testing and debugging. While developers write code on one main platform, they often want to debug and test it on many different platforms that they develop on software to in the field. Thus, virtualization makes it easy to do so by enabling a developer to run many operating system types and versions on just one machine. This resurgence in virtualization began in earnest the mid to late 1990s and was led by a group of researchers at Stanford headed by Professor Mendel Rosenblum. His group's work on Disco, a virtual machine monitor for the MIPS processor, was an early effort that revived VMMs and eventually led that group to the founding of VMware, now a market leader in virtualization technology. In this chapter, we will discuss the primary technology underlying Disco and through that window, try to understand how virtualization works. To run a virtual machine, an OS and its applications on top of a virtual machine monitor, the basic technique that is used is limited direct execution, a technique we saw before when discussing how the OS virtualizes the CPU. Thus, when we wish to boot a new OS on top of the VMM, we simply jump to the address of the first instruction be and let the OS begin running. It is as simple as that. Assume we are running on a single processor and that we wish to multiplex between two virtual machines, that is, between two OSs and their respective applications, in a manner quite similar to an operating system switching between running processes, a context switch. A virtual machine monitor must perform a machine switch between running virtual machines. Thus, when performing such a switch, the VMM must save the entire machine state on one OS, including registers, PC, and unlike in context switch, any privileged hardware state. They store the machine state to the to be run VM and then jump to the PC of the to be run VM and thus complete the switch. Note that the to be run VM's PC may be within the OS itself. The system was executing a system call, or it may be simply be within a process that is running on that OS. We get into some slightly trickier issues when a running application or OS tries to perform some kind of privilege operation. For example, on a system with software managed TLB, the OS will use special privilege instructions to update the TLB with a translation before restarting an instruction that suffered a TLB miss. In a virtualized environment, the OS cannot be allowed to perform privilege instructions because then it controls the machine rather than the VMM beneath it. Thus, the VMM must somehow intercept attempts to perform privilege operation and thus retain control of the machine. A simple example of how a VMM must interpose on certain operations arises when a running process on a given OS tries to make a system call. For example, the process may be trying to call open on a file, or may be calling read to get data from it, or may be calling fork to create a new process. In a system without virtualization, a system call is achieved with a special instruction. On MIPS, it's a trap instruction. On x86, it is the interrupt instruction with the argument x80. Here is the open library on TPST. Recall that a C code first makes a library call into the C library, which then executes a proper assembly sequence to actually issue the trap instruction and make a system call. So open push keyword mode, push tward flags and push toward path, move EAX5, push EX, and int ATH. On Unix-based systems, open takes just three arguments: int open, uh, path flags more. You can see in the code above how the open library call is implemented. First, the argument gets pushed onto the stack. You have more flags path. Then A5 gets pushed onto the stack. Then int ATH is called, which translates control to the kernel. T5, if you were wondering, is the pre-agreed upon convention between user mode applications and the kernel for the open system call and free BSD. Different system calls would place different numbers onto the stack before calling the trap instruction in and thus making the system call. When a trap instruction is executed, as we have discussed before, it usually does a number of interesting things. Most important in our example here is that it first transfers control to a well-defined trap handler within the operating system. The OS, when it is first starting up, establishes the address of such a routine with the hardware. Also a privilege operation, and thus upon subsequent traps, the hardware knows where to start running code to handle the trap. At the same time of the trap, the hardware also does one other critical thing. It changes the mode of the processor from user mode to kernel mode. In user mode, operations are restricted and attempts to perform privilege operation which uh, attempts to perform privilege operations or and attempts to perform privilege operations will lead to a trap and likely the termination of the offending process. In kernel mode, on the other hand, the full power of the machine is available and thus all privilege operations can be executed. Thus, in a traditional setting, again without virtualization, the flow control would be like what you see in figure B.1. So execute instructions, add load extractor, system call, trap to OS, switch to kernel mode, jump to trap handler. In kernel mode, handle system call, return from trap, switch to user mode, return to user code, and then resume execution. Okay, so when we want to do privileged operations, we switch to the kernel mode, do the privileged operation, and then switch back to the user mode. So what should the VMM do to handle the system call? The VMM doesn't really know how to handle the call. After all, it does not know the details of each OS that is running and therefore does not know what each call should do. What the VMM does know, however, is where the OS's trap handler is. It knows this because when the OS booted up, it tried to install its own trap handlers. When the OS did so, it was trying to do something privileged and therefore trapped into the VMM. At that time, the VMM recorded the necessary information. Now, when the VMM receives a trap from a user process running on a given OS, it knows exactly what to do. It jumps to the OS's trap handler and lets the OS handle the system call as it should. When the OS is finished, it executes some kind of privilege instruction to return from the trap, which again bounces into the VMM, and which then realizes that the OS is trying to return from the trap and thus perform a real return from trap, and thus it returns control to the user and puts the machine back into in user mode. The entire process is depicted in figures B.2 and B.3, both for the normal case without virtualization and the case with virtualization. So without virtualization, trap into OS trap handler, decode trap and execute appropriate system call. When done, return from trap. And then we have system call, process trapped, call the OS trap handler at reduced privilege, and then OS does the trap handler. OS try return from trap, do real return from trap, and then resume execution. As you can see from the figures, a lot more has to take place when the virtualization is going on. Certainly, because of the extra jumping around, virtualization might indeed slow down system calls and thus could hurt performance. You might also notice that we have one remaining question: what mode should the OS run in? It can't run in kernel mode because then it would have unrestricted access to the hardware. Thus, it must run in some less privileged modes than before. Be able to access its own data structures and simultaneously prevent access to its data structures from user processes. In the Disco work, Rosenblum and colleagues handled this problem quite neatly by taking advantage of the special mode provided by the MIPS hardware known as a supervisor mode. When running in this mode, one still does not have access to privileged instructions, but one can access a little more memory than when in user mode. The OS can use this extra memory for its data structures all as well. On hardware that doesn't have such a mode, one has to run the OS in user mode and use memory protection, page tables, and TLBs to protect OS data structures appropriately. In other words, when switching into OS, the monitor would have to make memory of the OS data structures available to the OS via page table protection. When switching back to the running application, the ability to read and write kernel would have to be removed. So OS page table, virtual address space, physical memory, and then machine memory. Okay, let's read what this is. Virtualizing memory. You should now have a basic idea of how processor is virtualized. The VMM acts like like an OS and schedules different virtual machines to run. Some interesting interactions occur when a privilege level change. But we have left out our big part of the equation. How does the VMM virtualize memory? Each OS normally thinks of a physical memory as a linear array of pages and assigns each page to itself or user processes. The OS itself, of course, already virtualizes memory for its running processes such that each process has the illusion of its own private address space. Now we must add another layer of virtualization so that multiple OSs can share the actual memory of the machine, and we must do so transparently. The extra layer of virtualization makes physical memory a virtualization on top of what the VMM refers to as machine memory, which is the real physical memory of the system. Thus, we now have an additional layer of indirection. Each OS Each OS maps to virtual to physical addresses via its per process page tables. The VMM maps the resulting physical mappings to underlying machine addresses via its OS page tables. Figure 4.p depicts this extra level of indirection. So OS page table VPN, virtual page number to physical frame number, so 0 to 10, and VMM from 3 to 6. This is machine frame number, right? In the figure, there is just a single virtual address space with 4 pages, each of which are wired. The OS uses its page table to map these pages to 3 underlying physical frames. Underneath the OS, the VMM performs a further level of indirection, mapping PFNs 3, 8, and 10 to machine frames 6, 10, and 5 respectively. Of course, this picture simplifies things quite a bit. On a real system, there would be EV operating systems running with V likely greater than 1 and thus VMM page tables. Further, on top of each running operating system, OSI, there would be a number of processes PI running and hence PI page tables within OSI. To understand how this works a little better, let's recall how address translation works in a modern paged system. Specifically, let's discuss what happens on a system with a software managed TLB during address translation. Assume a user process generates an address for an instruction fetch or an explicit load or store. By definition, the process generates a virtual address as its address space has been virtualized by the OS. As you know by now, it is the role of the OS with help from the hardware to turn this into a physical address and thus be able to fetch the desired contents from physical memory. Assume we have a 32-bit virtual address space and a 4 kilobyte page size. Thus, our 32-bit address is chopped into two parts. a 20-bit virtual page number VPN, and a 12-bit offset. The role of the OS with help from the hardware TLB is to translate the VPN into valid physical page frame number PFN and thus produce a fully formed physical address which can be sent to physical memory to fetch proper data. In the common case, we expect the TLB to handle the translation in hardware, thus making the translation fast. When a TLB miss occurs, at least on a system with a software managed TLB, the OS must get involved to service the miss, as depicted in figure 5.B.5. This is B.6. So load from memory TLB miss trap, OS TLB miss handler extract VPN from BA, do page table lookup if present and valid, get PFN, update TLB, return from tab, and then resuming execution. As you can see, a TLB miss causes a trap into OS which handles a fault by looking up the VPN in the page table and installing the translation in the TLB. With a virtual machine monitor underneath the OS, however, things again get a little more interesting. Let's examine the flow of a TLB miss again. When a process makes a virtual memory reference and misses in the TLB, it is not the OS TLB miss handler that runs, rather, it is the VMM TLB miss handler, as the VMM is the true privileged owner of the machine. However, in the normal case, the VMM TLB handler doesn't know how to handle the TLB miss, so it immediately jumps into the OS TLB miss handler. The VMM knows the location of this handler because the OS during boot tried to install its own trap handler. The OS TLB miss handler then runs, does a page table lookup for the VPN in question and tries to install the VPN to the FN mapping in the TLB. However, doing so is a privilege operation and thus causes another trap into the VMM. The VMM gets notified for when any non-privileged code tries to do something that is privileged, of course. At this point, the VMM plays its trick. Instead of installing the OS's VPN to PFN mapping, the VMM installs its desired VPN to MFN mapping. After doing so, the system eventually gets back to the user level code, which retries the instruction results in a TLB hit, fetching the data from the machine frame where the data resides. This set of actions also hint at how a VMM must manage the virtualization of physical memory for each running OS. Just like the OS has a page table for each process, the VMM must track the physical to machine mappings for each virtual machine it is running. These per machine page tables need to be consulted in the VMM TLB handler in order to determine which machine page a particular physical page maps to. And even for example, if it is present in a machine memory at the current time, the VMM could have swapped it to disk. Our discussion has centered around software managed TLBs and the work that needs to be done when a miss occurs. But you might be wondering, how does the virtual machine monitor get involved with the hardware managed TLB? In the system, the hardware walks the page table on each TLB miss and updates the TLB as need be, and thus the VMM doesn't have a chance to run on each TLB miss to sneak its translation into the system. Instead, the VMM must closely monitor changes the OS makes to each page table, which in a hardware managed system is pointed to by a page table based register of some kind, and keep a shadow page table that instead maps the virtual addresses of each process to the VMM's desired machine pages. The VMM installs the process shadow page table whenever the OS tries to install the process's OS level page table, and thus hardware chugs along, translating virtual addresses to machine addresses under the shadow table without the OS ever noticing, without the OS even noticing. Why are they calling it a table P.6? So alert from MTLBMS trap, VMM TLBMS handler, call into OS TLB handler, reducing privilege. So TLB mess handler extract VPN from VA, do table lookup. If present and valid, get PFN, update TLB. Trap handler unprivileged code trying to update the TLB. OS is trying to install VPN to PFN mapping, update TLB instead of VPN to MFN. Jump back into to OS, return from trap. Trap handler unprivileged code trying to return from a trap, return from trap, and then resume execution. Finally, as you might notice from the sequence of operations, TLB messes on a virtualized system become quite a bit more expensive than in a non-virtualized system. To reduce this cost, the designer of Disco added a VMM level software TLB. The idea behind this data structure is simple. The VMM records every virtual to physical mapping that it sees the OS try to install. Then on a TLB mesh, the VMM first consults its software TLB to see if it has seen this physical to virtual to physical mapping before. Now, what the VMM decide virtual to machine mapping should be. If the VMM finds a translation in its software TLB, it simply installs the virtual to machine mapping directly into the hardware TLB and thus skips all the back and forth and a control flow above. In many situations, it is good to assume that the OS cannot be modified in order to work better with the virtual machine monitors. For example, because you are running your VMM under an unfriendly competitor's operating system. However, this is not always the case, and when the OS can be modified, it may run more efficiently on top of on top of a VMM. Running a modified OS to run on a VMM is generally called paravirtualization. As the virtualization provided by the VMM isn't a complete one, but rather a partial one requiring OS changes to operate effectively. Research shows that properly designed para-virtualized system with just the right OS changes can be made to be nearly as efficient as a system without a VMM. Just like the OS doesn't know much about what application program really want and thus must often make general policies that hopefully work for all programs. The VMM often doesn't know too much about what the OS is doing or wanting. This lack of knowledge, sometimes called the information gap between the VMM and the OS, can lead to various inefficiencies. For example, an OS, when it has nothing else to run, will sometimes go into an idle loop, just spinning and waiting for the next interrupt to occur. It makes sense to spin like this if the OS is in charge of the entire machine and thus knows that there is nothing else that needs to run. However, when a VMM is running underneath two different OSs, one is idle and one is usefully running user processes, it would be useful for the VMM to know that one OS is idle so I can give more CPU time to the OS doing useful work. Another example arises with demand zeroing of pages. Most operating systems zero a physical frame before mapping it into a processor's address space. The reason for doing so is simple security. If the OS gave one process a page that another had been using without zeroing it, an information leak across processes could occur, thus potentially leaking sensitive information. Unfortunately, the VMM must zero pages that it gives to each OS for the same reason, and thus many times a page will be zeroed twice, once by the VMM when assigning it to an OS, and once by the OS when assigning it to a process. The authors of Disco had no great solution to this problem. They simply changed the OS to not zero pages that it knew had been zeroed by the underlying VMM. There are many other similar problems to be described here. One solution for the VMM user interface, a form of implicit information to overcome the problem, uh, is to use inference as an interface. One solution is for the VMM to use inference to overcome the problem. For example, a VMM can detect the idle loop by noticing the OS has switched to a low power mode. A different approach seen in para-virtualized system requires the OS to be changed. This more explicit approach, while harder to deploy, can be quite effective. Implicit information can be a powerful tool in layered systems where it is hard to change the interfaces between systems. But more information about the different layer of the system is needed. For example, a block-based disk device might like to know more about how file system above it is using it. Similarly, an application might want to know what pages are currently in the file system page caches, but the OS provides no API to access this information. In both these cases, researchers have developed powerful inferencing techniques to gather the needed information implicitly without requiring an explicit interface between layers. Such techniques are quite useful in a virtualized machine monitor, which would like to learn more about OSs running above it without requiring an explicit API between the two layers. Virtualization is in a rene- renaissance for a multitude of reasons. Users and administrators want to run multiple OSs on the same machine at the same time. The key is that VMMs generally provide this service transparently. The OS above has little clue that it is not actually controlling the hardware of the machine. The key control of the VMMs used to do so is the extent the notion of limited direct execution. By setting up hardware to enable VMM to interpose on key events such as traps, the VMM can completely control how machine resources are allocated by preserving the illusion that OS requires. You might have noticed some similarities between what OS does for processors and what VMM does for OSs. They both virtualize the hardware after all and hence do same for some of the same things. However, there is one key difference. With the OS virtualization, a number of new abstractions and nice interfaces are provided. The VMM level virtualization, the abstraction is ideal up to the hardware. While both the OS and VMM virtualize hardware, they do so by providing completely different interfaces. VMMs, unlike the OS, are not particularly meant to make the hardware easier to use. There are many other topics to study if you wish to learn more about virtualization. For example, we didn't even discuss what happens with I/O, a topic that has its own new and interesting issues when it comes to virtualized performance. We also didn't discuss how virtualization works when running on the side with your OS in what is sometimes called hosted configuration. Finally, hardware support has changed how platforms support virtualization. Companies like Intel and AMD now include direct support for an extra level of virtualization, thus obviating many of the software techniques in this chapter. Perhaps in a chapter yet to be written, we will discuss these mechanisms in more detail. Yeah, that was the last chapter I wanted to read. Should I read this deprecated chapter as well? It's about monitors. How long is this? There's also 13 pages. But it says deprecated though. Okay, this is not the physical monitor. This is something else. Around the time of concurrent programming was becoming a big deal, object-oriented programming was also gaining ground. And surprisingly, people started to think about ways to merge synchronization into a more structured programming environment. One such approach that emerged was monitor, first described by Per Bridge Hansen, later redefined by Tony Hoare. Okay, let's just read this. Let's read the dialogue first. So, Professor, so it's you again, student. I bet you are quite tired by now, being so old. Not that 50-year-old is that old, really. I'm not 50, I just turned 40 actually. But goodness, I guess you, being 20 something, student 19 actually. Professor, yes, 19, whatever. I guess 40 and 50 seem kind of similar, but trust me, they're not. At least that's what my 50-year-old friends tell me. Student, anyhow, Professor, yes. What we are talking about again, students, monitors. And not that I know what a monitor is, except some kind of old fashioned name for a computer display sitting in front of me. Professor, yes, this is a whole different type of thing. It's an old concurrency primitive designed as a way to incorporate locking automatically into object oriented programs. Student, why not include it in the section on concurrency then? Professor, well, most of the book is about C programming and the POSIX threads libraries, where there are no monitors, so there's that. But there are some historical reason to at least include the information on the topic, so here it is, I guess. Student, history. That's for old people like you, right, Professor Chris? Student, or take it easy, I get. But I can't wait until you take the final exam. So monitor class account, private, balance is zero, public, white deposit, amount, and withdraw. Okay, what's happening here? Now that this is a pretend class because C++ does not support monitors and hence the monitor keyword does not exist. However, Java does support monitors with with what are called synchronized methods. Below we will examine on how to make something quite like a monitor in both in C and C++, as well as how you use Java synchronized methods. This example, you may notice we have our old friend the account and some routines to deposit and withdraw an amount from the balance. You may also notice these are critical sections. If they are called by multiple threads concurrently, you have a race condition and the potential for incorrect outcome. In a monitor class, you don't get into trouble, though, because the monitor guarantees that only one thread can be active within the monitor at a time. Thus, our above example is a perfectly safe and working piece of code. Multiple threads can call deposit or withdraw and know that mutual exclusion is preserved. How does the monitor do this? Simple with a lock. Whenever a thread tries to call a monitor routine, it implicitly tries to acquire the monitor lock. If it succeeds, then it will be able to call into the routine and run the method's code. If it does not, it will block until the thread that is in the monitor finishes what it is doing. Thus, if we wrote a C++ class that looked like the following, it would accomplish the exact same goal as the monitor class above. Private mutex monitor. So public deposit, lock the monitor, update the balance, and then unlock. And then we withdraw. Like I want them to give Java examples. Withdraw amount, lock monitor. Thus, as you can see from this example, the monitor isn't doing too much for you automatically. Basically, it is acquiring a lock and releasing it. By doing so, we achieve what the monitor requires. Only one thread will be active within deposit or withdraw is desired. You might wonder why monitors were invented at all instead of just explicitly locking. At the time, object-oriented programming was coming into fashion. Thus, the idea was to gracefully blend some kind of key concepts into concurrent programming with some of the basic approaches of object orientation. Nothing more than that. Do we get more than automatic locking? Back to business, as we know from the discussion of semaphores, having just locks is not quite enough. For example, to implement the producer consumer solution, we previously used semaphores to both put threads to sleep when waiting for the condition to change, as well as wake up a thread when a particular condition has changed. Monitors support such functionality through an explicit construct known as a condition variable. Let's take a look at the producer consumer solution, here written with monitors and condition variable. The monitor class we have two routines, produce and consume. A producer thread would repeatedly call produce to put data into the bounded buffer, while a consumer class would repeatedly call consume. The example in a modern paraphrase of Hoar's solution. You should notice some similarities between this code and the semaphore based solution in the previous node. One major difference is how condition variables must be used in concert with an explicit state variable. In this case, the integer for entries determines whether a producer or consumer must wait depending on its state. Semaphores and contrast have an internal numeric value which serves the same purpose. Thus, a condition variable must be paired with some kind of external state value in order to achieve some end. Most important aspect of this code, however, is the use of two condition variables, empty and full, with respective wait and signal calls that employ them. These operations do exactly what you might think. Wait blocks the calling thread on a given condition. Signal wakes up the waiting thread. that is waiting on a condition. However, there are some subtleties in how these calls operate. Understanding the semantics of these calls is critically important to understanding why this code works. In what researchers in operating systems call or semantics. Yes, a somewhat unfortunate name. How do you pronounce this? The signal immediately wakes up one waiting thread and runs it. Thus, the monitor lock, which is implicitly held by the running thread, immediately is transferred to the working thread, which then runs it, either blocks or exits the monitor. Now that there may be more than one thread waiting, signal only wakes one waiting thread and runs it, while the other must wait for a subsequent signal. A simple example will help us understand this code better. Imagine there are two threads, one a producer and other a consumer. The consumer gets to run first and calls consume, only to find that full entries is zero, as there is nothing in the buffer yet. Thus, it calls wait and waits for a buffer to be filled. Yeah, I need a diagram for this. The producer then runs and finds it doesn't have to wait P0. Okay, it's this. Why don't this wait? Did they say figure? Okay, let's read again. Two threads, one a producer, one a consumer. The consumer gets to run first, calls consume only to find that full entries is zero, as there is nothing in the buffer yet. A bounded buffer, buffer max, fill use, full entry is zero, empty and full. So produce and consume. Produce elements. You're adding elements to the buffer. If full entries is max, then wait, but it's not max. So we just skip this. So buffer fill is right now. Don't we need to initialize fill as 0? So fill, so buffer 0 goes to, it's an element goes to buffer 0, and then fill is incremented. Then full entries plus plus. And then signal full. If you want to consume something from the buffer, we check if full entries is 0. Then we wait for the buffer to be full. Okay, so the first time it goes to consume, then the consumer gets to run first and calls consume only to find the full entries is 0, as there is nothing in the buffer yet. Thus it calls wait and waits for the buffer to be filled. The producer then runs and finds it doesn't have to wait. Okay, puts an element into the buffer. So the thread which is consuming sees that the full entries is 0. There are 0 full entries, and then it will wait. The producer, however, it will skip this and it will fill the buffer. But why can't we just use fill instead of full entries? I mean, it's not exactly full, it just has one element in it. Producer then runs and finds it doesn't have to wait, then puts an element into the buffer. It increments the fill index, and the full entry is count, called signal full. In Hoare semantic, the producer does not continue running after the signal, rather the signal immediately transfers control to the waiting consumer, which then returns from wait and immediately consumes the element produced by the producer and so on. Only after the consumer returns will the producer get to run again and return from the produce routine. What if we run produce so many times that we fill up the buffer and we never consume? What happens then? Tani, who wrote the solution above and came up with the exact semantics for signal and wait, was a theoretician. Clearly a smart guy too, he came up with the quick sort after all. However, the semantics of signaling and waiting, as it turns out, were not ideal for real implementation. As the old saying goes, in theory, there is no difference between theory and practice, but in practice, there is. The old saying is, in theory, there is no difference between theory and practice, but in practice, there is. Of course, only practitioners tell you this. A theory person could undoubtedly prove that it is not true. A few years later, Butler Lampson and David Riddle of Xerox were building a concurrent language known as MISA and decided to use monitors as their basic concurrency primitive. They were well known system researchers, and soon they found that Hoare semantics, which, while more amenable to proofs, were hard to realize in a real system. In particular, to build a working monitor implementation, Lamson and Redel decided to change the meaning of signal in a subtle but critical way. Signal routine was not just considered a hint. It would move a signal waiting thread from a block state to a runnable state, but it would not run it immediately. Rather, the signal thread would retain control until it exited the monitor and was descheduled. Given these new meso semantics, let us again examine the code above. Imagine again a consumer who enters the monitor and finds the buffer empty and thus waits. He finds it empty and then thus waits. Now the producer comes along and fills the buffer and signals that a buffer has been filled, moving the waiting customer from locked to full condition variable to ready. The producer keeps running for a while and eventually gives up the CPU. But Houston, we have a problem. Can you see it? Imagine a different consumer now calls the consume routine. It will find a full buffer and consume it. It will find a full buffer and consume it and return, setting full entries to zero in the meanwhile. Can you see the problem yet? Well, here it comes. Our old friend consumer one now finding gets to run. Wait. Uh, so let us again examine the code above. Imagine again consumer one who enters the monitor and finds the buffer empty and thus waits. Now the producer comes along and fills the buffer, signals that a buffer has been filled. Moving the waiting consumer from block on a full condition variable to ready. Right, so this consumer goes from block to ready, but it's not running yet. Producer keeps running for a while. Okay, so the producer who filled the buffer, the producer is still running, and eventually it will give up the CPU. And the consumer, it changed from block to ready, but before consumer one ran, consumer two is now calling the consume routine, and it will find a full buffer, consume it, and turn, setting the full entries to zero in the meanwhile. Can you see the problem yet? Well, here it comes. Our old friend consumer one now finally gets to run, and it turns from wait, exiting a buffer to be full, expecting a buffer to be full. Wait, but consumer 2 already used the wait call, right? No, wait. Consumer 2 did not reach here. Consumer 1 reached here. It was waiting. It became blocked and it changed from blocked to ready. Consumer 2 came, skipped this line, did all of this, and the full entries is now 0. Consumer 1, which was in a ready state at line C1, is going to run C2 and find that it is empty. Expecting a buffer to be full. Unfortunately, this is no longer true as consumer 2 snuck in and consumed the buffer before consumer 1 had a chance to consume it. Thus, the code doesn't work because on the same time between the signal and between the signal by the producer and the return from wait, consumer 1, the condition has changed. This timeline illustrates the problem. Fortunately, the switch from OR semantics to MESA semantics requires a small change by the programmer to realize a working solution. Specifically, when working a thread should reach at the condition it was waiting on because signal is only a hint. It's possible that the condition has changed and thus may not be in desired state while waiting thread runs. In our example, two lines of code must change lines P0 and C0. Wait, what's the change? Line P0 and C0. So producer, consumer, and consumer 2 full entry. Wait, consumer 1 full entry 0, blocked, producer full entry 0, and then it changes the full entry to 1. Condition 1 becomes ready. Consumer 2 changes the full entry to 0 because it consumes the buffer. Going back to consumer 1 using a buffer, but full entry is not 0. Full entry is 0. Now we change from if to while. So while full entries is max and while full entry is 0. Alright. So when it goes out of wait, in case it will check again in case any other consumer has used it. Not too hard after all because of this ease of implementation, virtually any system today that uses condition variables while signaling and waiting uses MESA semantics. Thus, if you remember nothing else at all from this class, you should just remember always recheck the condition after being moved in. Put it in simpler terms, use while loop and not if statements when checking conditions. Note that this is not always correct, even if somehow you're running a system with whore semantics. In that case, you will need to needlessly retest the condition and extra time. To understand a bit better why MESA semantics are easy to implement, let's understand a little more about implementation of MESA monitors. In their work, Lamson and Rattle describe 3 different types of queues that a thread can be part of at a given time: the ready queue and a monitor lock queue and a condition variable queue. Note that a program might have multiple monitors, classes, and multiple condition variable instances. There is a queue per instance of set time. While a single bounded buffer monitor, we thus have 4 queues to consider: the ready queue, a single monitor queue, and two condition variable queues. One for the full condition and one for the empty. To better understand how a thread library manages these queues, what we will do is show how a thread transitions through these queues and produce a consumer example. In this example, we will walk through a case where a consumer might be woken up but find that there's nothing to consume. Let us consider the following timeline. On the left, there are 2 consumers, 1 and 2, and a producer, in which line of code they are executing. On the right is the state of each of the 4 queues we are following for this example: the ready queue of the runnable process, the monitor lock queue called monitor, the empty and full condition variable queues. They're referring to this, right? Consumer 1, consumer 2, producer. So this is consumer 1, this consumer 2, and this producer. Monitor empty full. And this is a comment. I don't know what this is. Oh, full entry. So 0, this is 1. Producer, so producer, wait, condition 1, condition 1 waiting on full, switching condition 1 to produce, producer, producer updates full entries, producer signals, condition 1 now ready, switch. Now we switch here. Consumer 2 changes full entries, consumer 2 signals empty, consumer 2 done. Switch to 1, rechecks full entries which is 0, wait on full again. Other uses of monitors in their paper on Mesa, Lamson, and Rydell also point out a few places where a different kind of signaling is needed. For example, consider the following memory allocator. Figure D.7, many details are left out of this example in order to allow us to focus on conditions for waking and signaling. Turns out the signal wait code above does not require work. Can you see why? Allocator. Available. How much memory is available? So void allocate while size is more than available, then we wait. And then once we stop waiting, that memory uses the available size, so available becomes minus. So we subtract size from available because the new allocator is used that size. And whatever the allocator should do and return a chunk of memory. Now, and over here we have free. Available becomes plus size and signal C. Many details are left out of this example in order to allow us to focus on the conditions for waking and signaling. Imagine two threads called allocate. The first calls allocate 20, the second calls allocate 10. Right? No memory is available and thus threads call wait and block. Both threads call wait and wait. What do you mean no memory is available? What did we set the size to? Okay, let's say some other memories, other allocator used up all the memory and now there is no memory available. So then we wait. Sometime later, a different thread comes along and calls free and thus frees up 15 bytes of memory. Then signals it has done so. Unfortunately, wakes up the thread waiting for 20 bytes and then rechecks the condition, finds that only 15 bytes are available and then calls wait again. The thread that could have benefited from the free of 15 bytes is not woken. Samson and Redis suggest a simple solution. Instead of signal, which wakes a single waiting thread, they employ a broadcast which wakes up all waiting threads. Thus, all threads are woken. Right. So instead of signal, we use broadcast. In the example above, the thread waiting for 10 bytes will find 15 available and succeed in its allocation. And when it allocates, it will set this back to wait, right? And wait will undo the broadcast. Misa semantics using a broadcast is always correct as all threads should recheck the condition of interest upon waking anyhow. However, it may be a performance problem and thus should only be used when needed. In this example, a broadcast might wake hundreds of waiting threads only to have one successful continue while the rest immediately block again. This problem, sometimes known as a thundering herd, is costly due to all extra context switches that occur. Using monitors to implement semaphores. You can probably see a lot of similarities between monitors and semaphores. Not surprisingly, you can use one to implement the other. Here we show you how you might implement a semaphore class using a monitor. As you can see, wait simply waits for the value of a semaphore to be greater than 0. Semaphore is integer value, wait, while s is less than 0, we wait. S becomes minus, and then post S plus plus, and then signal. Okay, wait, somebody waits for the value of the semaphore to be greater than 0 and then decrements its value, whereas post increments the value and wakes up one waiting thread. It's as simple as that. To use this class as a binary semaphore, you can initialize the semaphore to 1 and then put wait post pairs around critical sections. And thus only have shown that monitors can use to implement semaphores. We have already mentioned above that we were using pretend monitors. C++ has no such concepts. We now show how to make monitor like C++ class and how Java uses synchronized methods to achieve a similar end. So here is a producer consumer code written in C++ with locks and condition variables. You can see in this code example that there is a little difference between the pretend monitor code and the working C++ class we have above. Of course, one obvious difference is the explicit use of a lock monitor. Most subtle is the switch to the POSIX standard thread condition call and thread condition wait calls. The buffer. Oh, this is the same as before. But this time we have this lock over here and a signal here and unlock here. They use both signal and locks. The wait thing also does the unlock, right? Unlock just unlock, but wait also unlocks, right? In practice, notice that when calling wait, one also passes in the lock that is held at the same time at the time of waiting. The lock is needed inside wait because it must be released when this thread is put to sleep and required before it runs to the caller. Interestingly, the designers of Java decided to use monitors as they thought it would be it. As they thought they were a graceful way to add synchronization primitives into the language. To use them, you just use the add key. Just add the keyword synchronized to the method or set the methods that you wish to use as a monitor. This code does exactly what you think it should, provide a counter that is thread safe. So where is the example? Oh, here is the example. Synchronize counter, provide public synchronized void increment, public synchronized void decrement, public synchronized integer value. This code does exactly what you think it should, provide a counter that is thread safe because one thread that is allowed into the monitor at a time, only one thread can update the value of C, and thus a race condition is avoided. In the original version of Java, a condition variable was also supplied with each synchronized class. To use it, you would call either wait or notify. Oddly enough, in this original implementation, there was no way to have two condition variables. You may have noticed in the producer consumer solution, we always use two for signaling a buffer that has been emptied and another for signaling that a buffer has been filled. To understand the limitations of only providing a single condition variable, let's imagine the producer consumer solution with only a single condition variable. Imagine two consumers run first and both get stuck waiting. Then a producer runs, fills a single buffer, wakes a single consumer, and then tries to fill again, but then finds up the buffer full. Thus, we have a producer waiting for an empty buffer and a consumer waiting for a full buffer. A consumer who had been waiting about to run because it has been woken. Consumer then runs and consumes the buffer when it calls notify, though it wakes a single thread that is waiting on the condition. Because there is only a single condition variable, the consumer might wake up the waiting consumer instead of the waiting producer. Thus, the solution does not work. To remedy this problem, one can again use a broadcast solution. In Java, one calls notify all to wake all waiting threads. In this case, the consumer would wake up a producer and a consumer, but the consumer would find that full entries is equal to 0 and go back to sleep, while the producer would continue. As usual, waking all waiters can lead to thundering herd problem. Because of this deficiency, Java later added an explicit condition class, thus allowing a more efficient solution to this and other similar concurrency problems. We have seen the introduction of monitors, a structuring concept developed by Bridge Hansen and subsequently Hoare in the early thir- uh, in the early 70s. Rendering inside the monitor thread implicitly holds a monitor lock and thus prevents other threads from entering the monitor, allowing the ready construction of mutual exclusion. We also have seen the introduction of explicit condition variables which allow threads to signal and wait, much like we saw with semaphores on the previous node. Semantics of signal and wait are critical because all modern systems implement mesosemantics, a recheck of the condition that the thread on when to sleep on is required for the correct execution. Thus, signal is just a hint that something has changed. It's the responsibility of the working thread to make sure the conditions are right for its continued execution. Finally, because the C++ has no monitor support, we saw how to emulate monitors with explicit pthread locks and condition variables. We also saw how Java supports monitors with its synchronized routines and some of the limitations of only providing a single condition variable in such an environment. All right, then. That was my last chapter with this. The last chapter I wanted to read. I will end the stream here then. And yeah, I will see what new book I will read. I think I'll start reading an open introduction to discrete math. I want to read, so my plan is to read discrete math and to to reread data structures. I've never read that on stream before. So yeah, I'm planning to read about about discrete math and yeah, I'll end this stream here then. Anyways, see you guys later. Bye.